To calculate the limit of n to the power of 3, nth root of 2 times 1 minus cosine 1 over n squared over square root of n squared plus 1 minus n without using L'Hopital's rule or Taylor expansion. Instead, we're going to use this well-known limit to prove this less well-known limit, and to use this kind of well-known limit to prove those kind of well-known limit. Not that well-known, but first of all, using this well-known limit, because 1 minus cosine x over half of x squared is equal to 1 minus, using double angle formula, cosine x is equal to 1 minus twice of sine squared half of x. In that case, we have twice of sine squared. Right? Sine squared half x is sine half x times sine half x. Right? Here we have half of half times half x times half x, right? Since we have 2 times 2, 4, 1/4. Therefore, we should multiply by 4. Right? So it's still the same thing, right? So 4 over 4 over 2, right? Half of x squared, same thing. Then sine half x over half x. And this sine half x over half x, they all approach 1. So 1 times 1 times, this is just 2, right? 2 and 2 cancel. So this eventually approaches 1, right, as x approaches 0. So I'm done with this limit. And I'm going to use this limit to prove this limit and that limit. Then we're going to use this limit and this limit to calculate this limit. So log 1 plus x over x. The reason it approaches 1 is because it is equal to log of 1 plus x to the power of 1 over x. Right? Logarithm rule, right? X at the bottom, that's what it means. And inside here, the inside function, right, as x approaches 0, 1 over x approaches infinity. So this inside, this guy approaches e. Right? So therefore, this whole thing should approach log e, that is 1, right, as x approaches 0. So I'm going to use this to prove this limit. Right. A to the power x minus 1. A to the power x minus 1 is equal to y. Then let's calculate x in terms of y. So a to the x is equal to 1 plus y. Take logarithm on both sides. Logarithm of this one is x times log a, right? Logarithm rule, take down the power, is equal to log of 1 plus y. So x is equal to log a at the bottom, log 1 plus y. So the original expression, a to the power x minus 1, is now y. Right? X is what? Is this. Log 1 plus y over log a. Right? Log a can be written on the top. Right? We multiply by log a. So y over log of 1 plus y. Right? Does y approach 0 as x approaches 0? X approaches 0. Y, yes. X approach 0, meaning y approach 0. In this case, same thing, right? Log of 1 plus some unknown over some other over the same unknown. That's this unknown approaches 0. Limit is 1, right? We have the unknown of y. Y approaches 0. So this definitely approaches 1. Right? So this whole thing should approach log a, right, as x approaches 0. So this limit is done. Now I'm done with this limit. Now moving on to the last limit. So I'm going to use the change of base, right? 1 plus x was the base, changed into base e. So this top becomes e to the power of log of this thing, right? Log of this thing, take down the power. Alpha times log of 1 plus x, right, and minus 1 over x, right? Over x. Now I'm going to multiply by both sides on both top and bottom by log of 1 plus x. Log of 1 plus x. So this approaches 1 as x approaches 0. Right. How about this? I'm going to treat log of 1 plus x as a whole thing, right? I'm going to treat log of 1 plus x is equal to y. As x approaches 0, y approaches 0 as well, right, obviously. So I just need to calculate the e to the power of alpha times y. Right? Alpha times y, right, to the power of y. The same thing. Minus 1 over y. Right? Like I said, y approaches 0. So I've proven a to the power of x minus 1 over x approaches log a as x approaches 0. Right? The only difference here, I have y. Y still approaches 0. Same thing, right? So this should approach log of whatever the base is. So log of whatever the base. E to the alpha is the base, right? That is alpha as x approaches 0, right? X approaches 0, y approaches 0. So meaning x approaches 0. This. So this approaches alpha, while this approaches 1, right? Log of 1 plus x over x approaches 1. So alpha times 1, still alpha. Right? Still alpha as x approaches 0. So I'm done with this one. So I'm done proving the limits of all of those limits. Now the main tool I'm going to use is called equivalence substitution. Meaning if we want to calculate the limit of x approach x naught of f of x times h of x, all we have to do is to show that if limit of x approaches x naught of f of x over g of x is approaching 1, then we can use equivalence substitution. Just simply substitute f with g. Right? In other words, this should equal to limit of x approaches x naught of g of x times h of x. The reason is simply because f of x times h of x is simply f of x divided by g of x multiplied by g of x. Right? The same thing. Divide, multiply, same thing. Times h of x. Right? Still the same thing. Like I said, if we can show the limit of f over g is 1, right? Then if we can work out the limit of g times h, then we can simply state that the limit of f times h must equal to limit of g times h, right? Because this is already approaching 1, so 1 times this limit, right, should be exactly the same. Equivalent substitution. So I'm going to use the notation. So equivalent substitution. I'm going to use the notation of this notation. right? I'm going to say sine of x is equivalent, sine x and x are equivalently infinitesimal. Equivalent infinitesimal, meaning limit of sine x over x is equal to 1. That's what I'm talking about. So likewise, 1 minus cosine x and half of x squared, they are equivalent infinitesimal, right, as x approaches 0. Likewise, if I want to use this, then I can say, okay, 1 plus x to the alpha minus 1 over, if I divide alpha over to the other side, I'm left with 1 on this side, right? So meaning the limit of this over x times alpha is equal to 1. So in other words, this thing over alpha, and if I times x, it will approach 1. In other words, this is equivalent to x, equivalent infinitesimal, right? If every time I see this expression, right, in, for example, in somewhere here, if it's multiplication or division, right? Multiplication or division, right? Division can be seen as a multiplication of reciprocal. So I can just substitute this just with x, right? Whenever I see 1 minus cosine x somewhere in the multiplication or division, I can substitute it with just half of x squared. Now let's use equivalence substitution to our desired sequence, right? So our desired sequence is now, let me just copy down the nth root of 2. Don't worry about this. In the end, it will approach 1. Right, copy down n to the power 3, and we can substitute this 1 minus cos with just half of x squared, right? What's x? It's 1 over n squared. Is it approaching 0? Yes, as n approaches infinity, right? So simply can be replaced by just half of 1 over n to the 4th, right? Raised to the power of 2. And that's what I have on top. What's on the bottom? Bottom, let me just square root of n squared plus 1 minus n, right? We're going to deal with this. So let's cancel out something. Right, cancel out 1 over half of the nth root of 2 times 1 over n. Right. Now I want to divide everything by n on both top and bottom, right? I have 1 over n squared, right? Then what do I have on the bottom, right? Minus n minus 1. And square root 1 over, inside the square root, I now should have 1 plus 1 over n squared, right? Square root can be written as the power of half, right? Now I can just use equivalence substitution, right? This power is alpha. Alpha this time is just half. X, what's x? X is just 1 over n squared, approaching 0, obviously. So as long as I can maybe divide by the power of alpha, right? So here I can divide by half. Then I do the same thing on the top, right? Divide by half. Half divided by half. It's gone. Now, this whole fraction can be replaced with just x. What's x? 1 over n squared, right? So bottom is just 1 over n squared. Top is just 1 over n squared and nth root of 2. Right? So 1 over n squared, 1 over n squared. Gone. As n approaches infinity, the nth root of any positive constant approaches 1. That's a well-known fact. Right? So approach is 1.